Okay. This is our first street, which is the microwave and antenna engineering. This one we are going to start. You know the syllabus. Right now we are talking about the. Actually, this is the introductory slide. We'll talk about the transmission line mainly. After finishing this one, then we'll go to the waveguides. Then we'll go to the microstrip lines. Then we'll go to the microwave resonators, the microwave network analysis. I think I will show you the microwave network analysis before the waveguides. Okay, before the waveguides, I'll show you the microwave network analysis, inshallah. And waveguide, waveguide and my microstrip lines, microstrip resonator. This will come one by one later. And finally, in the final, we'll discuss about the radiation and antennas. Okay, we'll discuss about the radiation and antennas in the final. And in that one, we'll discuss about the types of antennas and their applications, radiating field regions, radiation pattern, isotropic, directional and omnidirectional patterns, radiation power density, radiation intensity, beam width, directivity, antenna efficiency and gain, polarization, vector, effective length, effective aperture, equivalent circuit model, and corresponding parameters. Okay, those things will come at the final term, and at the final. Okay, for this one, for these topics, we have to look at several books. Actually, our main book is the second one, Fields and Waves in Communication Electronics, Simon Remo. That is our main book, first edition. Do you try to remember it? This is the first edition, Fields and Waves in Communication Electronics, Simon Remo. The book has had been written, has been published in the year 1965. So this book is a very old one. Almost 55 years ago, this book has been written. So this is the main book, and remember one thing: this you will get the latest versions now, but we do not want to take the latest versions. We do want to take the first edition, because first edition is the more flexible to understand. And we have another one, that is the Microwave Engineering David M. Poser 4th edition. That is the Microwave Engineering 4th edition, David M. Poser. Okay, that is another book. We'll look at it, and we have few more books. I'll give you the soft copy, but I do not have the soft copy of the Simon Remo book. Okay, we do have the soft copy of other books. So from the from this one, the Fields and Waves in Communication Electronics, I'll give you the scanned copy. That means the chapters, particular chapter. I'll give you the particular chapter, not the whole. I'll give you the particular chapter to check it out. Okay.
Yes. স্যার আমার কাছে থার্ড এডিশনে সাইমন রেমোর বইটা আছে, এটা কি হবে না স্যার?
না, থার্ড এডিশন আমি ইয়ে করে আমার সাথে মিলবে না তখন, বুঝছো? থার্ড এডিশন কি এতে কিনছো ফিল্ডস এন্ড ওয়েবসে?
জি স্যার, এটা ইয়েতে ছিল ফ্রি একটা, মানে স্যার গুগল ড্রাইভের একটা ইয়েতে ওইখানে আছে। এটা ফার্স্ট এডিশন ছিল, বাট থার্ড এডিশন নামাইছি আমি স্যার।
আচ্ছা, তুমি ফার্স্ট এডিশনটা নামাইও, ফার্স্ট এডিশনটাই আমরা ইয়ে করি আর কি।
ওকে
মানে যেটা হচ্ছে তোমার যখন আমরা পড়েছিলাম, আমাদের স্যারও ওইটা পড়াইছেন আর কি, ফার্স্ট এডিশন। এই কারণে আমি ওইটা পড়াই। আর ফার্স্ট এডিশনটাই মূলত ইয়ে আর কি, মানে বেসিক ক্লিয়ার করার জন্য ফার্স্ট এডিশনটাই বেটার।
ওকে স্যার,
ঠিক আছে, ওইটা নামাই নিও। আর যদি তুমি পুরো সফট কপি পাও, আমার ইয়ে করে দিও, সেন্ড করো।
আচ্ছা
কারণ আমার কাছে ইয়ে নাই, ফার্স্ট এডিশনটা নাই, যা আছে হার্ড
স্যার।
কপি।
আমি
ওকে ওকে, So this is the introductory slide. In the introductory, because the first class was the in the first class we have not discussed many things because as usual it was a introductory slide, introductory class. So I have not discussed many things, but today I'll have to discuss the basics of microwaves. Okay. So let's start. So what is the wave? See, in physics, wave is disturbance or oscillation that travels through matter or space accompanied by a transfer of energy. See, that is the definition of waves. That is the definition of waves. In physics, a wave is disturbance or oscillation that travels through matter or space accompanied by a transfer of energy. Understand? So it is a oscillation or disturbance which travel through the matter or the space which carry the energy. Energy will transfer or energy transfers through the wave. Okay. So that is a wave. And there are two types of waves are there, mechanical wave and electromagnetic waves. So, but two types of waves, but we are stick with the electromagnetic waves. Okay, so electromagnetic wave, that means it has the electric field and the magnetic field. The combination of both called together the electromagnetic wave. See, these are the example of EM waves, examples of electromagnetic waves. Radio waves, microwaves, infrared radiation, visible light, and ultraviolet radiation. These are the types of electromagnetic waves. Radio waves, microwaves, infrared radiation, visible light, and ultraviolet radiation. Okay. Radio waves, microwaves, infrared radiation, visible light, and ultraviolet radiation. These are the types of electromagnetic waves. So, but we are look at the only microwaves. When you read the communication engineering, then you will see all other things: radio waves, infrared radiation, visible light, ultraviolet radiation. But I'll tell you the spectrum range, in which range what situated. Okay. Now look at the microwaves. Electric field. The red one is the electric field. The blue one is the magnetic field. Those are perpendicular to each other. The electric field and the magnetic field are perpendicular to each other. Okay, those are the perpendicular to each other. Electric field and magnetic field are perpendicular to each other. And microwaves are electromagnetic waves, definitely. Those are electromagnetic waves. And the frequency range is 300 megahertz to 300 gigahertz. Remember this thing, the range of microwave is 300 megahertz to 300 gigahertz. 300 megahertz to 300 gigahertz. That is the frequency range of microwaves. Okay, wavelengths range in air. So if you look at the wavelength range is 100 centimeter to 1 millimeter. 100 centimeter to 1 millimeter. Wavelength range in air 100 centimeter to 1 millimeter. And frequency range is 300 megahertz to 300 gigahertz. Okay, 300 megahertz to 300 gigahertz. This is the frequency range. And wavelength range in air 100 centimeter to 1 millimeter. And microwave means very short wave. Microwave is the so what does it mean? Microwave means the very short wave. So if you look at the definition, microwave is the shortest wavelength region of the radio spectrum and a part of the electromagnetic spectrum. So if I ask you define microwave, so what you will say? So you'll say that microwave is the shortest wavelength region of the radio spectrum and a part of the electromagnetic spectrum. So it is a part of the electromagnetic spectrum. It is a part of the electromagnetic spectrum. Okay. So see, microwave is the shortest wavelength region of the radio spectrum and a part of the electromagnetic spectrum. So few things you have to remember from this slide, like it is the electromagnetic waves. Microwave is the electromagnetic wave, and the frequency range of microwave is 300 megahertz to 300 gigahertz. Wavelength range is 100 centimeter to 1 millimeter. And it is a very short wave, and this is the definition. It is the shortest wavelength region of the radio spectrum and a part of the electromagnetic spectrum. And it is a part of the electromagnetic spectrum. Okay, these things are you have to remember from this slide. Okay, so see the frequency band. High frequency band 3 to 30 megahertz, very high frequency band 30 to 300 megahertz, ultra high frequency band 300 to 1000 megahertz. L band 1 to 2 gigahertz, S band 2 to 4 gigahertz, C band 4 to 8 gigahertz, X band 8 to 12 gigahertz. Q band 12 to 18 gigahertz, K band 18 to 27 gigahertz, K band 27 to 40 gigahertz. V band 40 to 75 gigahertz, W band 75 to 110 gigahertz. Millimeter band 110 to 300 gigahertz. Millimeter band 110 to 300 gigahertz. See, these are the frequency ranges. So microwave starts from the ultra high frequency UHF band. Microwave starts from the ultra high frequency band. Okay, so microwave starts from the ultra high frequency band, which is 300 to 1000 megahertz. And other band, C, L band 1 to 2 gigahertz, S band 2 to 4 gigahertz, C band 4 to 8 gigahertz, X band 8 to 12, Q band 12 to 18. So these are the bands. Okay, these are the bands. Now see some properties of microwave. Okay, we have to see some properties of microwave. Okay, so electromagnetic radiation. So what are the properties of microwave? The property are electromagnetic radiation of short wavelength. It is a electromagnetic radiation of short wavelength. It can reflect by conducting surface like optical waves. Microwave can reflect by conducting surface like optical waves, like lights. And microwave current flows through outer layer of conductor. So it will flow through the outer layer of the conductor, and microwaves are easily attenuated. It can be easily attenuated. Microwave can easily attenuate it. And they are not reflected by ionosphere. Okay, look at the fifth term. They are not reflected by ionosphere. Microwaves not reflected by ionosphere. This term indicates that is why we do use microwave in the satellite communication. So if someone asks you, why do we use the microwaves in the satellite communication? So answer will be, they are not reflected by the ionosphere. That is why we are using microwave for the for the satellite communication. Okay, for the satellite communication. So this is the important one. So these are the properties of the microwaves. So try to understand those things. The first one, it is a radiation of short wavelength. It can reflect by conducting surface like optical waves, and microwave current flows through the outer layer of conductor. Microwaves are easily attenuated. Those are easily attenuated. They are not reflected by ionosphere. They are not reflected by the ionosphere. And advantages and limitations. Microwaves have large bandwidth. It has large bandwidth and it has improved directive properties, can be focused in a specified direction. Fading effect and reliability. Okay. Look at the advantages. These are the advantages. Microwave does have the large bandwidth. It has the large bandwidth. It has improved directive properties. It can be focused in a specified direction. Fading effect and reliability. Due to line of sight and high frequency, fading effect is very low. Due to line of sight, due to LOS, line of sight, and high frequency, fading effect is very low. Fading effect is very low. Transmitter receiver power requirement are pretty low at micro frequencies. So transmitter and receiver power requirements are pretty low. In the micro frequencies, transmitter and receiver power requirements are low at the micro frequencies. Okay. So these are the advantage of microwaves. And another one, what I have discussed earlier, microwave can propagate through the atmosphere, which range 300 megahertz to up to 10 gigahertz range. Microwave are capable to propagate through the atmosphere. For this reason, the astronomical research of space, we do use the microwave. This helps in astronomical research of space in the study of microwave radiations from the sun and the stars. This helps in astronomical research of space in the study of microwave radiations from the sun and the stars. Okay, so this is from the astronomical, this is for the astronomical research. Okay, so microwave band ranging from 300 megahertz to 10 gigahertz are capable of freely propagating through atmosphere. Microwave band ranging from 300 megahertz to 10 gigahertz are capable of freely propagating through atmosphere. This helps in astronomical research of space in the study of microwave radiations from the sun and the stars. Okay, microwave band ranging from 300 megahertz to 10 gigahertz are capable of freely propagating through atmosphere. This helps in astronomical research. Okay, so try to remember the range. At which range it is capable of propagating through the atmosphere. The range is 300 megahertz to 10 gigahertz. That is the range up to which microwave can propagate through the atmosphere. What is the advantage of this? That's why microwave used in the astronomical research to detect the radiation from the sun and stars. Okay, few more advantages, like since it has a high frequency, 300 megahertz to 300 gigahertz, that is why you can send more data through the microwave, and it has high bandwidth, higher speeds. High bandwidth, higher speeds. Okay, it has the high bandwidth as well as the higher speeds. And since it has a short wavelength, microwaves use smaller antennas. So it has a short wavelength, so it does use the short antennas. Okay. So because of that short wavelength, microwave use smaller antennas. So what is the advantage of a smaller antennas? It can produce a more focused beam. It can produce a more focused beam. For the short antennas, it can produce a more focused beam. Okay. These are the advantage of this. So first advantage, because of high frequency, more advantage actually. Because of high frequency, more data can be sent. We can send the more data, and it will have the high bandwidth, higher speeds. Because of the short wavelength, since it has a short wavelength, microwave use smaller antennas. Smaller antennas produce a more focused beam. So smaller antennas produce a more focused beam. Okay. So these are the advantage. But microwave has some limitations also. Disadvantages. Microwave have some disadvantages. One disadvantage is they require no obstacle is present in the transmission path. Same. They require no obstacle is present in the transmission path. No obstacle is present in the transmission path. That is the first one. Second one, the cost of implementing the communication infrastructure is high. Microwaves are susceptible to rain, snow, electromagnetic interference. These are the disadvantage, yes, of microwave communication. They require no obstacle is present in the transmission path. The cost of implementing the communication infrastructure is high. Microwaves are susceptible to rain, snow, electromagnetic interference. Okay. Microwaves are susceptible to rain, snow, and electromagnetic interference. So you do understand the first one, they require no obstacle is present in the transmission path. That means if you place a obstacle, if you do place any thing in front of the microwave communication, then it will be affected. The microwave communication will be affected. Okay, we do have a experimental setup. If we put anything in front of the communication path or line of sight path, then in the receiving end we do not get the proper signal. And the cost of implementing the communication infrastructure is high. The cost is high. The cost of implementing the communication infrastructure is high. The cost of implementing communication infrastructure is high. That means when you try to set up the microwave communication thing, then it will cost higher. And microwaves are susceptible to rain, snow, electromagnetic interference. See, microwaves are susceptible to rain, snow, electromagnetic interference. That means microwaves are susceptible to rain, snow, and electromagnetic interference. So if there is rain, or if there is snowfall, or if there is any other electromagnetic thing, then it will be hampered. The microwave communication will be hampered. Okay. And see, that is the functional block diagram of a communication system. That is a functional block diagram of a communication system. So I think you know that well. At first, we need what? We need a channel which could be wired or wireless. In the microwave communication, it is a wireless. See, in the microwave communication, it is a wireless channel. Some of your friends are trying to join. Okay. Okay. So input signal, audio, video, data, input transducer, then transmitter, then channel, then receiver, then output transducer. In the meantime, you will get some. You will have to pass it through the channel, wired or wireless. It is wired or wireless. Okay, wired or wireless channel. So what kind of channel microwave is? Microwave is wireless channel. And remember one thing, microwave require line of sight communication. Line of sight communication. Okay, that is the necessity of microwave. It is the line of sight communication. See this part is the electrical system. Transmitter, channel, and receiver. This part is the electrical system. Okay. See this figure. In this figure, we have seen that on the Earth surface, there are transmitting in antenna and an and a receiving antenna. So when the communication occurred on the earth surface, that is the surface wave. Sometimes it goes through the antenna to antenna, that is the direct wave. That is the direct wave. And sometimes it reflected by the ionosphere, that is the sky wave. And microwaves, microwave millimeter and microwave and millimeter wave, those goes through the satellite communication. Those can be passes through the ionosphere. Those are passes through the ionosphere, and we get the satellite communication. Okay, we get the satellite communication here. Antenna and wave propagation. Antenna and wave propagation. So see here, some kind of waves are there: surface wave, direct wave, sky wave, and the microwave, which we do use on the satellite communication. Sometimes we do require repeaters. Sometimes we need repeaters for terrestrial communication. That is 50 kilometer at 25 feet antenna. Repeaters. We need the repeaters to continue the microwave communications. See here, see the figure. It is another antenna which is repeater, which can be used for the terrestrial communication. 50 kilometer at 25 feet antenna. Okay. We need the repeaters for the terrestrial communication. 50 kilometer at 25 feet antenna. Okay. So at which distance after the 50 kilometer, and height of the antenna is 25 feet antenna. Okay. after the 50 kilometers, we do use a repeater to continue the microwave communication. Okay. So remember these things, this kind of wave: surface wave, direct wave, sky wave, and microwave. Okay, another term which is the waveguide. So what is the waveguide? It is a hollow metallic tube of uniform cross section for transferring electromagnetic waves by successive reflections from the inner walls of the tube. It's called the waveguide. Okay. That is the waveguide. A hollow metallic tube of uniform cross section for transmitting electromagnetic waves by successive reflections from the inner walls of the tube is called the waveguide. So inner wall, see, conductive wall is the inner wall. Okay, it works in the inner wall. So we do have the waveguide in our lab. Okay, I can show you the waveguides. Okay, so we need the waveguide. The thing is, why we do need this one? Electromagnetic waves at frequencies greater than 3 GHz, transmission through cables become difficult. So if we have the EM wave greater than 3 gigahertz frequency. So transmission through cables become difficult because this is due to losses in the solid cable and the dielectric used to support the cable. So why? Because the solid cable has some losses and we need the dielectric to support the cable. So we use waveguide, which is a hollow metallic. So we use waveguide, which is a hollow metallic. So this is due to losses in the solid cable and the dielectric used to support the cable. Okay. So why we need the waveguide? Because if you do use a solid cable, then there will be some losses. To avoid the loss, we use the hollow metallic. Why a solid cable has some losses? Because it does have the dielectric material inside the cable for supporting it. That's why we do use the hollow metallic waveguide, which has the which is hollow inside the metal. So some basic features of the waveguide. Like waveguides are used to carry energy from one equipment to another. We can use the waveguides to carry energy from one equipment to another. Like antennas, transmitter power, like in antennas, transmitter power to antenna and microwave signal from antenna to receiver. In this case, we use the waveguide. Transmitter power to antenna and the microwave signal from antenna to receiver. We'll see this later. Okay. Or let me show you one thing, since it is animation is possible. Say transmitter power to antenna. Okay, like say like this. We have the source. We have the source. Then we have the waveguide. That is the antenna. That is the antenna. That is the waveguide. So from source to antenna, we need the waveguide. Again, say if we have another antenna to receiver, we need another waveguide. Say this is the receiver, so we need another waveguide. Okay. See, here the use of waveguide. Here the use of waveguide. Source to antenna, waveguide. Okay. And waveguides are made from copper, aluminum, or brass. Waveguides are made from copper, aluminum, or brass, and the metals are extruded into long rectangular or circular pipes. The metals are extruded into long rectangular or circular pipes. That means it could be rectangular waveguide or maybe a circular waveguide. The energy to be transmitted is injected from one end of the waveguide through probes. So how we can transmit the energy? Through probes. We transmit the energy through probes. The electric and magnetic field of signals bounce off the walls back and forth. The electric and magnetic field of signals bounce off the walls back and forth. Okay, the signals bounce back and forth. Okay. So these are the features of waveguide. And electromagnetic fields confined in the waveguide are TEM, TE, TM, and hybrid. These are the types of waveguides, types of modes inside the waveguide. EM field configuration can be determined from Maxwell's equations. This configuration can be determined. We can determine the EM field configuration, electromagnetic field configuration from the Maxwell's equation. And there are a number of configurations, and each configuration is known as mode. Possible modes are transverse electromagnetic, transverse electric, transverse magnetic, hybrid. These are the modes. Okay, we'll discuss it later. Okay, so to find out the mode, we have to follow the Maxwell's equations. From the Maxwell's equation, and we can find out the electromagnetic modes. Okay, so I think this is enough for today, right?
Yes, sir.
I think this is enough for today.